Okay, we're back to our original format now. So, I mentioned earlier during that discussion about phonocardiograms that there was that S1 and S2 heart sound that was caused by the closure of the atrioventricular and the pulmonic and aortic valves. So this is our lub-dub of our physiologic heart sounds. And I'm going to play this overhead. The sound quality might not be fantastic, but whatever. Lub-dub, lub-dub. Now, this is S1 and S2. That lub-dub sound effect that you heard, that was the result of those physiological heart sounds. That S1, that lub, is the closure of the mitral and tricuspid valves. That second heart sound, dub, is going to be the closure of the aortic and pulmonic heart sounds. Those heart valves, excuse me. Now, this is not required by Cambridge, but I am going to tell you this anyway, because why not? If you just want to know what's necessary for Cambridge, you can skip ahead in the video. An S1, a split S1, there is no physiological splitting of S1 normally, but there is a pathological splitting of S1, which can result from electrical conduction issues in problems such as right bundle branch block. And we'll discuss what that means in a moment. What a right bundle branch is, so a blockage in your conduction system in the heart. And a split S1 sounds something like this. Blooper reel. Come on. There we go. Alright. So, an S2, there is physiological splitting of S2, which can be accentuated with inspiration. So when you breathe deeply, in particularly tall, skinny folks, this will increase the venous return to the heart, and it will delay the closure of the pulmonic valve. But you can also have pathological splitting of S2, which can occur from a conduction abnormality. And that one will not be made worse when you breathe in deeply. And so that's going to sound like this. All right. So, moving forward, we're going to talk for a moment about, we're going to start next about the conduction of the heart. And first we're going to decide on a series of terms. Myogenic contraction. This is a contraction initiated by the myocyte cell instead of an outside occurrence, such as a stimulus by a nerve innervation. Depolarization is the loss of polarization. So especially the loss of a difference in charge between the inside and the outside of the plasma membrane of a muscle or a nerve cell, due to a change in the permeability and migration of sodium ions to the interior of that cell. So when you have a lot of ions inside and outside of the cell, when you suddenly switch what ions are inside and outside of the cell, that will be depolarization. The polar nature of what ions are in and out of the cell. Conductivity. We're only talking about the biological definition of conductivity, not the chemical definition. Now, conductivity in the biological sense is the quality of living matter responsible for the transmission of and progressive reaction to stimuli. Now, here's some hints about what Cambridge expects from you in terms of usage of language. Cambridge wants you to use the phrases wave of excitation or impulses. The phrasings that will not get you certain the phrasings that is not going to get you acceptance from Cambridge. You won't get points for using these phrases. The word signal, wave, pulse, message, or nerve impulse, all these things are specifically cited as being wrong. So nerve impulse is especially wrong because there are no nerves, as we stated. It is a myogenic contraction. It is coming from the muscle itself with no nerves involved. So all of these words are imprecise we want these words, which are more precise. All right, so this is an anatomical drawing of our heart. This is a cartoon drawing, not the heart itself, because live hearts don't really stick well to a electronic board. So we have near the upper portion of our right atrium the sinoatrial node. The sinoatrial node is the primary pacemaker of the heart. This, through a slow leakage of sodium ions, will eventually depolarize, and that will cause a sudden explosive influx of calcium ions. That influx of calcium ions is going to start a chain reaction that will send a wave of excitation, buzzword, throughout the entirety of the right and left atrium, depolarizing the entirety of the right and left atrium, causing contraction in the right and left atrium. Now, this depolarization, this wave, will be blocked by the atrioventricular ring. The atrioventricular ring is a ring of non-conductive tissue in between the atria and ventricle. Now, this wave of depolarization is going to stimulate the atrioventricular node right here. The atrioventricular node is going to pass that impulse from the sinoatrial node, that stimulation from the sinoatrial node, along the bundle of His, which is a connection between the atrioventricular node, and it is a pass-through fiber through the atrioventricular ring down into the ventricular portion of the heart. Now, this causes a time delay. That time delay is about 0.1 seconds. That 0.1 second time delay has the following effect. It allows for the heart, the atria of the heart, to contract, and then the ventricles will contract. This is important because if the atria contract and the ventricles contract at the same time, then the atria contracting will basically prevent blood from flowing from the atria into the ventricles. It will basically slam shut these valves and prevent any more blood from flowing from the atria into the ventricles. 80% of the blood from the atria has already flowed into the ventricle. 20% of that blood flows into the ventricles during atrial contraction, atrial systole. So it's about 80% before atrial contraction, 20% the remainder after. So that 0.1 second delay allows the remaining 20% of blood flow from the atria to the ventricles to occur. If they both contracted at the same time, only 80% of flow would occur. So atrioventricular node passes the impulse from the sinoatrial node to the atrioventricular node through the bundle of His, bypassing the atrioventricular ring into the right and left bundle branch Purkinje tissues, down the interventricular septum. The interventricular septum here. So the interventricular septum here is already diverging into the right and left bundle branches. So the right and left bundle branches are here and here. So this is Purkinje tissue, as the British call it. I call it Purkinje fibers, and I will call it Purkinje fibers until the day I die. However, if you see it as Purkinje tissues, don't be surprised. So this Purkinje fiber material that is the right and left bundle branches will carry this impulse from the bundle of His down the interventricular septum toward the apex of the heart, allowing contraction of the ventricles to start at the apex of the heart, and then spreading the contraction along these Purkinje fibers and contracting the heart ventricles from the bottom up. So this contraction occurs along the ventricular walls as it spreads through the Purkinje fibers, contracting the ventricle walls from the bottom to the top, like emptying an almost finished tube of toothpaste, squeezing out the last little bits of it. Because your exit of blood through the heart exits through the vessels out the top of the heart right here. So you are squeezing from the bottom out. So this actually makes sense when we look at our electrocardiogram. Remember again that we had our P wave. Our P wave was our atrial contraction, our atrial depolarization, excuse me. The atrial depolarization fires a wave of depolarization. And then we had our QRS, Q, R, S. That, if I can draw it here. So we had our P wave. And then we had that little 0.1 second pause as it moved through the PR interval. So we had our P wave, our PR interval, that little pause. And then we had the Q, R, S. Q, R, S. And then we have our T wave as the ventricle repolarizes. Now that is an exaggerated T wave. That probably means somebody had a heart attack in the past. But, well, actually, that would mean somebody had a heart attack in the past, because that's a raised T wave. That's an ST elevation, but whatever. Nerd jokes. Anyway, so the T wave is ventricular repolarization. We won't see P wave, we won't see atrial repolarization, because the atria is tiny compared to the ventricle. Most of the heart is ventricle. So we're going to see ventricular repolarization, but we won't necessarily see atrial repolarization. All right? So this is how our electrocardiogram fits in with the conduction that we see in our heart. All right? So we're squeezing from the bottom up. And this is how our conduction works. Now, things that you should know. The wave of depolarization spreads across the network of cardiac muscle fibers that brings about systole, the contraction of the heart muscle, and the ejection of blood from the heart. Fibers will not fatigue. Fibers do not get tired. Muscle does. There is a long refractory phase in heart muscle fibers. It's about 250 milliseconds. That probably won't get you any additional points. It's just something neat. All right? Now, the intrinsic pacemakers of the heart, interestingly enough, your SA node has the fastest rate of pacing, about 60 to 100 beats per minute, average 75 beats per minute. Your AV node has a slightly slower pace. Your Purkinje system has a rate of about 20 to 40 beats per minute. So, in the event that your SA node is not functioning, your AV node can take over and start firing instead. And if your AV node is not functioning, your right and left bundle branches can start firing on their own. But your heart rate will be significantly slower each time. And if your SA node is not functioning, or if you're out of sync or out of time, you will probably have an arrhythmia of sorts, and you really should get that checked out. That's not a good thing. You should really go see somebody about that, like a good cardiologist. Look one up. Seriously, look one up. All right. Now, when the SA node depolarizes and sends that wave of excitation throughout the heart, that causes what's called overdrive suppression. Overdrive suppression resets that sodium channel leaking of all the other systems. It sends all that, it sends a wave of excitation throughout the entire conduction system and resets everything. So all of those timers will reset. And the process starts again. So as soon as one timer fires, all the timers will reset back to 0 and start over. Now, we're actually going to take a short break here and cut the video off before I said now, just there.